This video deals with vibrations and waves. All right, you might remember Hooke's law. We talked about this once before. F is equal to kx. Well, we're going to be using a special kind of form of this equation. F is equal to minus kx. I'll get to that minus sign in a minute. K, if you recall from before, is a spring constant. Here we're going to give it a sort of a more general name, a deformation constant. X would be the amount of deformation, or actually the displacement from the equilibrium position. We've got like a metal rod here, and the equilibrium position is right here in the center. So that would be X, the displacement from the equilibrium position. Okay, so now the negative sign. So while this object is displaced all the way in this direction, there is a force on it toward the equilibrium position, which would be that way, but the displacement from the equilibrium position would be measured that way. And if you looked at this particular side over here, the force would be this way, the force that tends to take this strip and bring it back to the equilibrium position, where again the displacement is measured this way. So the displacement and the force are always in the opposite direction. Okay, so we saw previously the potential energy stored in a spring is 1/2 kx squared. We're going to be using the same equation for this more general situation where this doesn't necessarily have to be a spring, although it could be, but it's just an object that is undergoes this periodic or vibratory motion. And by the way, what that means is that when this thing is released, the path of this metal strip is going to repeat itself at regular time intervals or periodically. All right, two other terms that I think we've mentioned before, and these are also going to be very important in this module, and that's period and frequency. And period is the time for one complete vibration or oscillation. The unit is time, usually in seconds, although it could be minutes or other units of time. Frequency is the number of oscillations per unit time, and the unit here is a hertz. A hertz is a cycle per second. Very importantly, period and frequency are reciprocals of each other. T equals 1 over F, F equals 1 over T. So here's an example. Computers have a clock signal that are used to synchronize all operations. The frequency are on the order of 2 gigahertz. You've probably seen this number before in reference to computers. What is the period for one of these clock cycles? Well, T is just equal to 1 over the frequency. The frequency is 2 gigahertz, which is 2 times 10 to the 9th cycles per second. Take the reciprocal of that, you get 5 times 10 to the minus 10 seconds. By the way, this cycle here usually just drops out of the units. You might say seconds per cycle, but it's usually just written as seconds. And then that is 0.5 nanoseconds. The motion of the object that is vibrating or oscillating is called simple harmonic motion. And we've got some examples of this simple harmonic motion down here. We've got a mass that's on a spring, and it's oscillating horizontally on a frictionless surface here, back and forth. Okay, so first of all, the motion here is periodic, and it can be described by this equation F is equal to minus kx, where the force is directly proportional to the displacement from the equilibrium position. Definition here, amplitude is the maximum displacement from the equilibrium position. That's called capital X being the maximum displacement from the equilibrium position. and the velocity is greatest at the equilibrium position and 0 at the amplitude positions. Okay, so let's look a little bit more closely at these diagrams here. So notice right here, we've got this mass. It's displaced all the way to the right. X is equal to capital X. That means that it's maximum displacement from the equilibrium position. Notice at that point, the force is maximum, but the velocity at that point is 0. Okay, now the object continues to move to the left here. Now it is at the equilibrium position. At that point, the force is 0, because x here is 0, and its velocity is maximum. It's negative Vmax because it's moving to the left. Okay, it moves all the way to the left. Now it's at the amplitude position on the other side here, the negative side. So x is equal to minus x, minus capital X. Again, the force is maximum. The velocity here is 0. And now it goes through the equilibrium position once again. X is equal to 0. This time it's moving to the right. And so now the velocity is plus Vmax. And now it comes back again and it goes toward the left. So the object is just going to continue to oscillate back and forth here as long as it's on a frictionless surface. Okay, this is energy of a simple harmonic oscillator, an object that is oscillating back and forth. We want to derive a couple of equations, but they do require some explanation, so I wanted to run through them with you. All right, so first of all, the kinetic energy and the potential energy of an object as it oscillates has to stay constant. As long as it's a frictionless surface, all that's going to happen is there's going to be a conversion between potential and kinetic, and back and forth, back and forth. So, mathematically, that would say that 1/2 mv squared, the kinetic, must be equal to plus 1/2 kx squared, which is the potential, has to stay the same. Okay, now, we can take these two equations, take these two expressions, and set it equal to 1/2 k capital X squared, because this is the potential energy at maximum displacement. And at maximum displacement, the object is at rest, and so it has no kinetic energy. Okay, so if this is true, we can solve for the velocity, and we get this expression. Notice this is under the square root sign, so this is plus minus, and I'll mention that in a minute. Okay, a little algebra here. We're going to remove this from the radical sign. It still has to be under the square root sign. And we're going to multiply both the numerator and denominator by x squared. And in doing that, we can do little algebraic manipulations and come up with this expression right here. You should be able to do that on your own. Okay, now, but since 1/2 mv squared, this would be the maximum kinetic energy when the potential is 0, must be equal to the maximum potential energy when the kinetic is 0. So this must be true, and therefore we can solve for Vmax, and we get this. And now we can take this expression right here and substitute Vmax right here. And so now we have the velocity is equal to plus or minus Vmax times the square root of 1 minus the displacement squared divided by the amplitude squared. This will allow us to compute the velocity of the object at any point in time, as long as we know its displacement here and what its maximum velocity might be. Notice, by the way, when the object is at the displacement, so in other words, this lowercase x would be the same as this capital X, they would be the same. this would be 1. 1 minus 1 is 0, so V would have to be 0, which is what we've been saying all along, that when the object is at that equilibrium position, its velocity is 0. All right, we've got a 6-part problem here that's going to demonstrate just about all of these concepts that we just spoke about. All right, so we've got a spring, and it's stretched 0.150 meters, 1.3 kilogram mass is gently suspended from it. Then the spring is set up horizontally, just like in our diagram before, with a 0.3 kilogram mass resting on a frictionless table. Mass is then pulled 0.1 meters from its equilibrium position and released, so it's going to oscillate back and forth. Okay, here's what we want to calculate. First of all, the spring constant, B, the amplitude of the horizontal displacement, C, the maximum velocity, D, the velocity when the spring is 0.05 from the equilibrium position, E, the maximum acceleration. We hadn't talked about that before, but you'll see that's pretty straightforward. The total energy, the kinetic energy, and the potential energy at half amplitude. Okay, easier than it sounds. First of all, the spring constant. Okay, so the spring constant is equal to, K is equal to F divided by X. We're just interested in the magnitude of this spring constant here. I didn't include the minus sign. So we took the 0.3 kilogram mass and we hung it on the spring and it stretched at 0.15 meters. So this was the force, 0.3 kilograms times 9.8. That's how much the spring stretched. So there is the spring constant, 19.6 newtons per meter. Okay, part B, the amplitude of the horizontal oscillation. Well, that's easy because the spring was pulled back 0.1 meters from the equilibrium position and then released. So that's got to be the amplitude right there, 0.1 meters. Okay, C, we want to calculate the maximum velocity. Okay, this is the equation that we had on that previous slide. Vmax is equal to the square root of K m divided by capital X. This is the spring constant. This is the mass, 0.3 kilograms. And then capital X here, remember the capital X is the amplitude, maximum displacement. That's 0.1 meters. We saw that there. Okay, so we worked through the math there. And the maximum velocity would be 0.808 meters per second. Okay, now part D, we want to find the velocity when the spring is 0.05 from the equilibrium position. So that's at half amplitude. Okay, so V is equal to, we had this equation again in the previous slide. So we calculated Vmax up here, that's 0.808 meters per second, times the square root of 1 minus, there's the 0.05, that displacement where we wanted to compute the velocity. Capital X is the amplitude, 0.1, and this is plus or minus 0.7 meters per second. Remember, that's plus or minus because it's going to go through that point, moving to the right, and then as it comes back to the left. So as it moves to the right, the velocity will be positive, to the left it will be negative. Okay, now E, the maximum acceleration. Well, we can get that from Newton's second law. A is equal to F divided by m. Remember, F equals ma. So F is going to be the maximum force. That's going to be the spring constant times that amplitude divided by m, the 0.3 kilogram mass. So it's the maximum force, and this is the mass, and of course maximum acceleration is going to result from the maximum force. Okay, so we solve for A, and that's 6.53 meters per second squared. Okay, now the total energy, well, the total energy we can get by 1/2 K capital X squared, where this capital X is the amplitude. And so that's 1/2 the spring constant we computed way up here. And this capital X, that's the amplitude, that's 0.1 meters. That has to be squared. So that is 0.098 joules. And then finally, G, the kinetic and the potential energy at half amplitude. Well, PE is equal to 1/2 K X squared. Whoops, looks like I forgot the square there. So that's 1/2 times the spring constant and the 0.05 meters. That's the half amplitude. That would have to be squared. And so the units, I believe this answer here is correct. I just forgot to put the square sign up there. So that is 0.0245 joules. And now the kinetic energy should be equal to the total energy, which we calculated back up here in F, minus the potential energy. Okay, so this is 0.098 joules, this is 0.045 joules, so we can subtract this from this, and we get 0.0735 joules as being the kinetic energy.